You don't try and go into space and up to the moon and Mars and build space stations and so on so you can escape the Earth when you've messed it up. It is the opposite. The idea is that by going into space, building infrastructure, ultimately accessing resources in space, you save the Earth, because the Earth is the best place in the universe because we evolved on it and it's unique. So the first question is, what is space? And that is a very good question. The 1 minute answer is we don't know. So one of our theories is that space and time, for that matter. So I should say, back in 1905, Einstein realized that space and time are not separate, but they're woven together into something that's often called the fabric of the universe, or more technically, space-time. But we now suspect, or at least we have a theory, that space-time emerges from something deeper, which is just basically quantum entanglement. So we think that there is a description of our universe which is just bits of information, basically, or qubits to be more technical, quantum bits of information that are entangled together into some sort of network. So space and time don't exist in that network, and then space and time emerge from that deeper theory. This is cutting edge physics, but it's one of the pictures that we have for what space and time might be. So there you go. What is space? It's also a thing that, it's the distance between stuff that you throw about, whatever. Right.
Counter arguments when we say we've seen nothing, therefore, as far as we can tell, there's nothing out there. You could say, well, what if the civilization that evolved is far ahead of us? What if the space probes are the size of an iPhone?
Right.
Well, it's kind of a reasonable thing to say, actually. Because
sure.
Why would you not, if you can build a little thing,
right.
It's easier to send around the galaxy than a big thing.
Yeah.
So why would you not, as you said, these ultra intelligent quantum computers, why would they not be tiny?
Right.
So you could say that. So you could say, well, that maybe they are. Maybe they're all over the solar system, but they're the size of phones and we wouldn't have seen them. And so, yeah. Okay.
Yeah.
You would have to concede that. So we're just saying that the way that we've looked for energy signatures, for example, of civilizations, you tend to look for big things because that's all we can see. And we don't see any big things. We don't see any big structures. We don't see any evidence of spacecraft and all that kind of stuff. But I could make an argument that, well, why would the spacecraft be big?
What is the best bit of evidence for alien life? We don't have any evidence for alien life is the answer. So in the past, we've landed missions on Mars, for example, the Viking missions in the 1970s. There was some suggestion that there might be some chemical reactions that looked a bit like life, and then it turned out that it probably wasn't, because it's very difficult to distinguish geology and chemistry from biology when you don't know what the kind of biology is that you're looking for. And so the answer is we don't have any evidence of alien life, of life beyond Earth, but we're looking. So that's the answer. And then everyone will whinge about that. We'll go, what about that flying saucer that landed in Chicago or something? And I'll say, I don't believe it did.
The sun will not form a black hole. When it runs out of nuclear fuel, it will collapse, and there's something that can stop it collapsing. So it's called a white dwarf star. It's a beautiful calculation, by the way, that. Something called the Pauli exclusion principle. So electrons don't want to be close together, roughly speaking. So as you squash the thing, the electrons get closer together, and so they separate away from each other and go into smaller and smaller little regions of space because they're trying to stay away from each other. But there's also something called the uncertainty principle. So as you confine them into smaller regions, you start jiggling around faster and faster. And ultimately you can reach a limit where they're essentially trying to jiggle at the speed of light, and they can't. So there's a limit to how much pressure that process can exert. And it turns out it's 1.4 times the mass of the sun. You could have worked that out, not knowing that stars exist. What is the biggest lump of stuff that can be held up by this jiggling of electrons? It turns out it's 1.4 times the mass of the sun. Then you look into the sky and there's none more massive than 1.4 times the mass. The sun will not. If civilizations are common, or even slightly common, then there should be civilizations ahead of us.
Yes.
Because there's been so much time.
But wouldn't you want to see what that's like?
Yeah, I mean, we've been
so compelling.
You imagine the timescales. We've been around as a civilization. Let's give it, say, 40,000 years. I don't know how long our civilization has been around. Let's say that. The galaxy is pretty much as old as the universe. It's 13 billion years worth of time. So the idea that there are no civilizations arose, 100 million years ago, 200 million years ago, 1 billion years ago. And imagine what they'd be like if they'd survived. I mean, we've been around, we've had science for, let's say, since Newton or Copernicus, 500 years at most. And look what we've done. We've gone beyond the solar system with Voyager. We've walked on the moon. We're about to go to Mars, I would think. So we're about to begin colonizing our own solar system. So we've done that in 500 years. So imagine a million years in the future.
What's going to wipe out humans first? If I was to guess, I would say humans. And that's not supposed to be a joke. I think that the biggest threat to our civilization is us. So we have complete control over that, but it might not help us, which says something about our stupidity. Beyond that, threats from space. So if a comet came in from the outer solar system, as they do, and it happened to be aligned with Earth, it happened to hit Earth, then there's nothing we could do about it at the moment. Most of the asteroids, the big asteroids that cross the Earth's orbit, we've mapped, but there are a few maybe that we haven't. We're looking, so we're actively trying to do that. And if we see that one of those big asteroids might collide in the future, then we've got a bit of time, 10, 20 years, whatever it is, so we might be able to do something about it. We're going to have to leave the Earth at some point and spread out into the solar system and beyond. If we manage to do that, and we're at the point now where we're just about to start, I hope. So we're not far off being able to travel, build moon bases and then travel to Mars. We're quite a long way off going from Mars beyond the solar system maybe. We're a long way off doing that. But at some point, if we do that, then nothing's going to wipe us out.
This word meaning that we used earlier, that we all understand but can't define, is that a emergent property that has to emerge if you've got something that's intelligent enough to replicate itself and live and, as you said, be the... I don't know the answer, but it's worth considering that this thing, emotion, meaning, love and fear and all those things are just the things that happen when you are intelligent.
Right.
I don't know the answer to that, but it could possibly be. It's not necessarily true that life is temporary, because you could imagine a situation as you go into the far future. Let's imagine that we continue for 1 million years or 1 billion years as a civilization. Imagine what we could do. It is possible that life can get so advanced in the universe that it can start to manipulate the universe itself. So, or at least stars. You could he said you could imagine, for example, just imagine, really wild speculation, but imagine life gets so advanced that it can start to change the destiny of a star. Maybe it could start to add material into the star or something, whatever. So we don't know how to do that or if it's possible, but imagine it could. Then the evolution of stars life would matter in the sense that it could start to change the way that the universe behaves on a large scale in the future.
Is time travel possible? Great question. It's kind of obvious to say it's possible into the future because, of course, that's what we're doing. We're moving into the future. It then gets interesting because you say, well, why do we have to go into the future? Why can't I stop going into the future? Well, you can vary the rate at which you go into the future relative to someone else. For example, if I was to get in a rocket now and accelerate off, even at 1g, right, just a sort of acceleration I could take, and head off and end up traveling relatively close to the speed of light, and let's say go to the Andromeda galaxy, and then which is 2 million light years away from the perspective of the Earth, and then turn around and come back again. If I go close enough to the speed of light, I could arrange it so I would age, let's say, a year on the outward journey and a year on the inward journey. And you could do that calculation. But 4 million years would have passed on Earth. So I would come back on that journey 2 years older, but I'd arrive at the Earth 4 million years in the future. So that's special relativity. That's Einstein's theory published in 1905. Not even the theory of gravity. So time travel is possible into the future, and it's inevitable that you travel into the future, and you can vary the rate you go into the future relative to someone else by the way that you travel around. In the past, Einstein's special theory of relativity from E equals mc squared, that thing in 1905 says no, you can't, because of the geometry of space and time themselves. his general theory of relativity, where space and time can be curved. That's his theory of gravity. The correct thing to say is that we can imagine distortion, geometries is the best way to say it. We can imagine geometries of space and time. Wormholes would be an example, where if you could go through them, you could travel into the past. However, we don't understand enough. So you can calculate these things, but whether or not they're possible to make is an open question. Most people think not. And the last thing I'll say, Stephen Hawking wrote a very famous paper called the chronology protection conjecture. And conjecture is important. So he conjectured that whatever the ultimate laws of quantum gravity are, they will be such that you can't build time machines that you can use to travel into the past.
On alien life, on life outside of this planet. Is this something you think about?
Yeah, I think there must be. Even in the solar system, I would not be surprised if we find microbes on Mars or on some of the moons of Jupiter or Saturn where there's liquid water.
Like Europa.
Yeah, and the reason is that if you think about, the reason I think that, and it's a guess, is because if you look at the history of life on Earth, then, so Earth formed and it was just there was no life. It was a ball of rock. And almost as soon as it cooled down, we see evidence of life. So certainly 3.8 billion years ago, possibly even further back than that, we see evidence of life on Earth. So somewhere along the line, geochemistry, active geochemistry became biochemistry on Earth. And we have some idea, that if you get gradients of temperature and acid and alkaline and the conditions that are naturally present on the surface of oceans, then complex carbon chemistry spontaneously happens.
Will we ever travel at the speed of light? No. So that's a simple answer. Anything that has mass cannot travel at the speed of light, but anything that is massless, that has no mass, has to travel at the speed of light. So photons, which are particles of light, for which, by the way, Einstein got the Nobel Prize, essentially, for something called the photoelectric effect back in 1905. So Einstein didn't get the Nobel Prize for relativity. He got it for this idea that you can think of light as a stream of particles hitting something and firing electrons out of it. So it's called the photoelectric effect. The way we understand physics at present, photons travel at the speed of light, not because they're light, but because they have no mass. So it should really be called the speed of massless particles. And that's built into Einstein's theory. It was subsequently realised, basically. So will we ever travel at the speed of light? No, unless you have no mass, in which case you have to.
Yes.
As you said, the most incredible thing, I just retweeted that and said, brilliant engineering. The number of tweets I got back saying that space is fake. I don't understand what it means. Space is fake. I don't even know what that means. But I got quite a lot of it. It's fake.
I went down a hashtag space is fake rabbit hole one night online. It has something to do with biblical stuff. They think that there's a firmament that's over the earth, and they think that the lights are dangled in the sky.
Oh, it's that.
So it's just the earth is a disc.
Dome.
Yeah, the earth is a disc, and that you can't get through the firmament, and that there's like an ice wall, and that's why you can't travel around Antarctica.
I love this.
Imagine all the astronomers, all the astrophysicists, all NASA, China, every space agency, they're all in cahoots.
But why?
And no one spilled the beans.
Prove to a flat earther that the world is round. I always say that I would hit them over the head with Newton's Principia. Because the implication, can you imagine if every time you get on a plane and fly somewhere, then the person who's in charge of the plane is part of a vast conspiracy that's trying to deceive you? Just imagine that. Right? How nervous would you be on the plane if the people that are flying it are actually just keeping you in the dark about the real nature of reality? How does that make you feel? You'd never get on a plane again. That would be great, because then when I go on holiday, I never bump into a flat earther because they don't travel.
They've been observing collisions of black holes.
Collision of black holes.
There are two black holes, and they were about 30 times the mass of the sun each. And they were orbiting each other and spiraling in towards each other. At one point, they were approaching each other at 1/3 the speed of light. And they accelerated to 2/3 the speed of light in 1/10 of a second, and then hit each other. And the explosion, the energy release, was something like 50 times the power of all the stars in the observable universe for a tiny fraction of a second. It's an unimaginably violent event.
Favourite fact about the universe? This is an easy one, I think. It's the size of the universe. The bit we can see which is what's called the observable universe, has about between 1 and 2 trillion galaxies in it, depending on how little tiny galaxies and big galaxies, but it's let's say 1 trillion-ish, something like that. And that is only a small patch of the universe that exists, so we're sure of that. Whether the universe is infinite in all directions, we don't actually know, but as far as we can tell, it could be. So my favourite fact about the universe is that it might be infinitely big.
If you look at the surface of the moon, for example, it's covered in craters, and that was caused, they all seem to hit about the same time, and it's about 3.8 billion years ago or so. And that's called the late heavy bombardment. So we know that if you look at cratering rates on Mars and on the moon, it all seemed to happen in this, not all, but a big peak around that time. And that seems to be correlated with Neptune moving outwards in the solar system and into the Kuiper Belt, basically, or towards the Kuiper Belt, and causing all sorts of havoc, and everything comes into the inner solar system. So those things happen. But it didn't happen when life was established on the Earth.
Doesn't this all give you an existential crisis? Yes and no. Because an existential crisis, it suggests, I suppose, that we question our own existence, doesn't it? That's what an existential crisis would be. Or at least you ask the question, what's the meaning of it all? Why are we here? I've got it written on my T-shirt, actually. Existence, what does it matter? And that's an Ian Curtis lyric. So I would say, yeah, listen to Joy Division. Is my answer.
There was a group of scientists that were speculating that it's possible that octopi had come from somewhere else. Some frozen eggs had actually come from somewhere else and landed on Earth. And these are like legitimate scientists who are contemplating, not morons.
So panspermia doesn't have to be unlikely.
Right.
I mean, for example, you might have seen the other day we found an Earth rock on the moon.
Yes.
Well, it's back on Earth now because the Apollo astronauts brought it back, didn't they? It's 4 billion years old or something like that.
One of the oldest rocks ever found.
Yeah. So we know that material gets transferred between planets. And so it's not inconceivable that microbes could survive that journey. We know that microbes can survive in space, for example. So that isn't mad. But with the octopus, I hadn't heard that. But the thing is that the octopus is still extremely similar biologically to us. I mean, the differences are negligible. So it's still got the same energy system with things like ATP and DNA and all that stuff. It's all very, very similar. Yeah, so
although so alien as well.
They're not, though. You know, that's the thing about an octopus. That's why I'm surprised about it, because they're not that alien.
What would happen if Earth or a human fell into a black hole? It depends on the mass of the black hole is the technical answer. So if it's a small black hole, by which I mean just, a few times the mass of our sun, then you get ripped apart by the tidal gravitational forces before you actually fell in. So as you approach the event horizon of the black hole, it becomes very nasty. But for the very big black holes, so like the one we have a photograph of, we've got 2 photographs actually. One of the one in the centre of the Milky Way, and one in the centre of a galaxy called M87, which is a very big one. It's something like 6 billion times the mass of the Sun. So a supermassive black hole in M87. It's 55 million light years away, that one. And if you fell towards that one, then, as far as we know, you would fall across the horizon into the interior of the black hole, and you'd be unaffected. You wouldn't notice as you fell across the horizon. And then you'd have something like, I can't remember the exact number, but it's something like 30 hours-ish inside the black hole until you approach the singularity, which is in your future when you cross the horizon. So it's not something you can avoid. It's like trying to avoid tomorrow. You can't do that. So you go to the singularity, which is, in Einstein's theory, the end of time. And just before you get there, you get spaghettified, which means you get stretched in one direction and squashed in the other, and even your atoms get ripped apart, and then you go to the end of time. So that's not nice. However, if you put quantum mechanics in, which goes back to Stephen Hawking's work in the 1970s, then we can start debating about what the horizon is, and there are certain ideas that you might get when viewed from the outside. You might it might appear you get incinerated before you cross the horizon, and all your ashes come back out into space again. But from your perspective, it seems that you wouldn't get incinerated. From your perspective, you'd go inside, and then you get spaghettified. And then the question is, do you get vaporized or spaghettified? And the answer might be both, which is called black hole complementarity, which is all very complicated. So it's one of those things. Again, ultimately, the answer to what would happen if Earth or a human fell into a black hole is, for a big black hole, we don't really know. But for a small black hole, you would get ripped to bits before you fell across the horizon.
What does a black hole do? A way of thinking about this, empty space isn't empty. It has a rich structure. The vacuum of space has a structure. And the black hole, it disrupts that structure. And the result is photons, essentially, but what's called Hawking radiation, is emitted from the black hole. Stephen Hawking gave an analogy. A way to picture the quantum vacuum is that you can imagine particles coming in and out of existence all the time in the vacuum. You can kind of picture it like that. You can have the situation where one of these particles is on the inside and one is on the outside. We know what's happening to the one on the inside. It's going to the singularity. So the other one is basically made real and escapes. The point is that this particle has been shaken out of the vacuum. What particle's been emitted? It's a temperature. That means it's losing energy. That means it has a lifetime. And that means one day it will be gone and space will be all nice and normal again, right? All you will have left will be the Hawking radiation that's been emitted over these eons of time. There's any purpose to the universe. I don't think there's any point to our existence. But the fact that we exist at all is worth celebrating. You don't need to add anything else. We emerged single-celled organisms. Probably before that, we emerged as some chemical reactions in hydrothermal vents, probably down in the deep primordial oceans of ancient Earth. And over 3.8 billion years, we've come to the point where we can sit and think about the stars and have conversations like this. Is that not enough? I think it's a reminder. Can we just leave it there? Why does there have to be a point? There isn't a point. I don't think there's a point to that, but it's worth celebrating.
Is the multiverse real? This is not. How am I supposed to answer? I've got all these right, and every one of these questions: is the multiverse real? The answer is it's very real as a possibility. For example, there's something called the inflationary multiverse. So one of our best theories of how our universe got to be the way that it is that before the Big Bang, then space and time still existed, and space was stretching very fast. It's a theory called inflation. And then that period of time draws to a close, so that the expansion rate, this incredibly fast expansion rate, slows down, and kind of the energy driving it collapses, changes form or state, and that's what we call the Big Bang. So the Big Bang is the end of inflation. Extensions of that, called eternal inflation, say or suggest that maybe that collapse, the end of inflation, maybe it doesn't all stop at once. So you're to picture patches of this rapidly expanding space, they're sort of collapsing and making big bangs, which make universes. And so that the process is called eternal inflation, because for all we know, it could have been going on forever in a sense, and would be going on now, if that was correct. So we would just be a bubble in this sea, an infinite sea of universes, of which we're a single bubble, and that's called the inflationary multiverse. Quantum mechanics does appear to suggest that really there are an infinite number of universes. So every possibility for every interaction that happens has a probability of it. It's like rolling a dice, and you could say, well, I roll a dice and it comes up a 3, but it could also be a 2 or a 4. And basically, the many worlds interpretation of quantum mechanics is that there's a universe in which every dice roll happens. So you get an infinite number of copies of you, for example, in this inflationary multiverse. Not the inflation, the many worlds interpretation of quantum mechanics.
Is that the one that the Marvel multiverse would fit into? That second one, or is that...
Yeah, so I think, although there are issues with the Marvel multiverse, in technical issues, the thing is that these universes very rapidly, unless it's something like a quantum computer or something, they're very rapidly what's called decohere. So they become separated from each other. So whether you could travel between these different branches of reality is. So is that another controversial thing to say? Have I just upset the Marvel fans now? I don't know whether I've done that.
Most simulations of the solar system, if you put other planets in, they tend to get thrown out by gravitational interactions. So there is a sense in which our solar system has got as much stuff in it as it could have. So the planets are nicely spaced. And you're right, given the mass of them, that depends on how close another planet can be before the interaction goes wrong and it gets thrown out into the intergalactic space or something, because planets do that. We know that planets get thrown out of solar systems by gravitational interactions. Again, it points to the fact that solar systems are not stable over long periods of time. They're not like clockwork things. They're not like, Newtonian clockwork and it just goes on forever. They're not like that. They evolve and planets can shift orbits.
Why is time different on different planets, like in Interstellar? So that's an easy question to answer. It's Einstein's theory of general relativity. As you come closer to a planet, then your time, so let's say you have a watch and you look at the watch, then you'll see the watch tick at the normal rate, 1 second per second, and you won't see anything unusual. But from the perspective of someone far away, that watch will be ticking more slowly than their watch. And it's really to do with the distortion of space and time in the vicinity of the planet. So the general rule is if you go to something that's very massive, so you approach a very massive planet or even a black hole, then as you go there, from the point of view of someone far away, they will see your time tick more slowly. So that's I was going to say basic general relativity. Should we leave it at that? Everybody should know a bit of general relativity.
Interesting, though, that if you ask astronomers, so you say, what's the probability of other civilizations being out there? Then they will point, for example, to the new data from the Kepler Space Telescope, which tells us that there are probably around 20 billion Earth-like planets in the Milky Way galaxy, in the sense that they're small rocky planets in what's called the habitable zone around stars.
The Goldilocks.
Around main sequence stars like the sun. So 20 billion. So maybe 1 in 10 stars in the sky has an Earth-like planet around it, potentially.
Like, that seems to me to be like one of the biggest, like, Hail Mary wishes, like hoping that you're going to find a radio signal from a galaxy far, far away that has intelligent life
for me now, a galaxy. So that's a lot. So you think 20 billion? Well, surely life must have arisen on some of those. The answer is probably yes, I suspect. We may find life on Mars in the next 10 years, but it'll be microbes. So the question then becomes, well, how likely is it for simple life, if it arises, to make its way into a civilization? Close to the speed of light, then distances shrink from your perspective. And the one number I always have in my mind is at the Large Hadron Collider at CERN, the protons go around the ring, which is 27 kilometers in circumference, and they go around at 99.999999% the speed of light. At that speed, distances shrink by a factor of 7,000. And so that ring is something like 4 meters in diameter to the protons. So according to laws of physics, if you can build a spacecraft that goes very close to the speed of light, you could traverse to the Andromeda Galaxy, and therefore the time it takes to get there, in principle, in a minute. However, the downside is if you came back to the Earth at that speed to tell everybody what you'd found, at least 4 million years would have passed on the Earth. We could, in principle, explore the galaxy and beyond, but getting to chat to everybody about what you found is forbidden.
Explain Schrodinger's cat with the honesty box. So the idea with Schrodinger's cat is if you have this...
I have a cat here for you, by the way.
There's a cat. Right? So I get this cat and I put it in a box, and I have a radioactive nucleus in the box. And if it decays, the nice way to say it is it releases a sleeping potion. But in its original form, it releases poison. And so if it decays, it releases some poison, which kills the cat or puts it to sleep. And it could wake up again at some point, depending on how sensitive you are. So it's either dead or it's not, depending on whether this thing decays or not. There's a probabilistic prediction for whether this thing is decayed or not. In just pure quantum mechanics, the nucleus is what's called in a linear superposition of states. So it's sort of some probability of being decayed plus some probability of being not decayed, and that's how you describe the nucleus. So that would suggest that's how you describe the cat. So the question is the correct description of this cat both alive and dead with some different probabilities that can change over time? But is that the correct description? And then you open it, of course, you see that it's one or the other. And so the question is that nonsense? Or the modern interpretation, especially the many worlds interpretation, would be that there's a universe where this thing is decayed and the cat's in, and I open this up and I see that it's alive or dead. So there's a universe in which I see it alive and a universe in which I see it dead. And the whole thing is just a big ensemble of probabilities called a wave function. So it was initially a kind of thing to say, well, this is a bit weird. It's got weird implications, quantum mechanics. And ultimately, it does have weird implications. And so that's it. So let's say it's the sleeping version, shall we, just to be all right. So that's Schrodinger's cat.
light doesn't travel particularly fast over cosmological distances, 186,000 miles a second. That means that as you look out to even nearby objects, closest object you can see with the naked eye, the Andromeda galaxy, if you look at that, about 2 million light years away, it means you see it as it was 2 million years in the past. You look at more distant galaxies, 10 million light years away, 10 million years in the past. So you could ask the question, are there objects that are so distant that the light travelling from them began its journey close to the Big Bang itself? Is that possible? And the answer is yes. And that light was first detected in the 1960s. It's called the cosmic microwave background radiation. The idea is, how far can I look? In every direction. You can look about 13.8 billion years into the past, back to the origin of the universe. It's on this diagram here. That is the furthest we can see. But at that moment, the universe is expanding and cooling, and it becomes cool enough for atoms to form.
Should we try to save the Earth instead of trying to get off it? They're linked. It's a very serious question, this. It's really important to say that nobody I've spoken to, and certainly my opinion, is that you don't try and go into space and up to the moon and Mars and build space stations and so on so you can escape the Earth when you've messed it up. It is the opposite. The idea is that by going into space, building infrastructure, ultimately accessing resources in space, and all the good things you can do in space, drug development, developing semiconductors, all sorts of industries that we can imagine in Earth orbit, you save the Earth. Because the Earth is the best place in the universe because we evolved on it and it's unique. So the idea of going into space is not to mess the Earth up and then escape it. It is exactly the opposite. I was involved in a discussion yesterday, actually. It was really interesting. And one of the experts in the space economy said to me that really we shouldn't think of the space economy as space. We should think of it as the economy. And so, because it's not far, right? It's just 100 miles up there. So it's about we're in London now, so it's about the distance from London to Birmingham. If you go from London to Birmingham, but you go that way, you end up somewhere where you can do stuff that is useful and it can produce economic growth. It can produce things like interesting drugs, for example, medicines and things which are not easy to build on Earth and so on. So you should think of space now not as a separate thing, but as a place where there's an opportunity to do stuff that benefits us all here on Earth, and that's the challenge.
The whole budget of CERN is about the same as the budget of a medium-sized university. It's about $1 billion a year. What's it done, though? Well, we invented the World Wide Web. A lot of the medical imaging technology that we use comes from CERN. It's pioneered the use of these very high field magnets, which is what it needed. So it's engineering at the edge. And engineering at the edge generates spin-offs and expertise to get used in other fields. So there's cancer treatment, so-called hadron beam therapy. So if you've got a brain tumour now, it's quite likely that you'll have one of these targeted particle beam therapies, which is like very highly targeted sort of chemotherapy. It's not chemotherapy, it's just radiation that you can target in a beam into your head and attack the tumour. And those are particle accelerators. So most particle accelerators today are in hospitals and in medicine.
Wow.
But they came from doing particle physics. Fly to Australia from LA and you have to go quite a long way around the edge of the Earth. Or you could tunnel straight through and get there quicker, right? So you can, that's a wormhole.
Jamie's got a little graphic up there.
So you can do that in Einstein's theory. You can write down that geometry and there it is. So the first question is, can you make it? And as we said, we don't think that stuff exists.
Right.
There's a second set of bits of theoretical work, which are, if you had a wormhole, then what would happen if you tried to travel through it? And what seems to happen is that they become unstable the moment that anything tries to go through. So you get kind of a feedback of stuff going through and through and through and through. And so it collapses. The answer is we don't fully know, but most physicists think that even if they existed, they would be unstable. And as soon as you even try to transmit information through them, send a bit of light through, then there would be this sort of feedback and they'd collapse.
Does the Big Bang disprove the existence of God? No. I mean, I don't know why. It's kind of the opposite, actually, isn't it, in some sense? Because very quickly, historically, Georges Lemaitre, who's often described as the father of the Big Bang, was a priest as well as a mathematician. And he was delighted that Einstein's theory certainly appears to suggest that there could have been a beginning. Einstein didn't like that. He wanted the universe to be eternal. But Einstein's theory is strongly suggestive of a beginning or an end. And Lemaitre, as a priest, was happier with that, because if you think about what a beginning is, you could call it in that language a moment of creation. So actually, historically, Lemaitre was more predisposed to accept that the universe might have a beginning, because he saw that as a more of a suggestion that there could be a God, because then you have a thing as a creator. So, it's kind of historically interesting.
In a God, right? I mean, what you can say if you're a cosmologist, what you should say is, where we know that the universe was very hot and dense 13.8 billion years ago. We don't know how it got hot and dense. We don't even know, actually, if the universe had a beginning in time. Don't know.
Science doesn't rule out the existence of a creator.
No, but in the sense that I just said, that I think we're overstepping the mark. I do not believe there's any evidence for a creator. However, I don't like the antagonism that occurs or is produced by this question. The point is that the correct thing to say is we don't even know whether the universe had a beginning. I don't even know whether it was eternal. Nobody does. So that was the point I was making. I think we're stepping into an area where we don't really need to visualize the scale of the universe. There are roughly 2 trillion galaxies. 2 trillion. 2,000 billion galaxies. And each galaxy is, let's say, around the size of the Milky Way. Some are bigger, some are smaller, but the Milky Way has 400 billion stars in it. It takes light over 100,000 years to cross a galaxy. And there are 2 trillion of them in the piece of the universe we can see. And we're very sure that that piece that we can see is a small bit of what may be an infinite universe beyond. We don't know, actually. And I always say, don't get worried about that, because nobody can picture it.
Rank the planets from best to worst. I'm going to piss everybody off and say Pluto's the best, and that's going to really annoy everybody because it got demoted. So we'll have Pluto as the best one, because then we can have an argument about whether it's a planet or not. After that, then the Earth, surely, it's kind of an obvious thing to say, but obviously the Earth is the best because it's the place that we evolved on. It's the only place we know, not only in the solar system, but in the entire universe, for sure, that life exists. So it's clearly the best planet. Beyond that, if we're going to live anywhere else in the solar system on a planet, then it has to be Mars, because we can't live on Mercury because it's too hot or too cold. It's actually a strange place because it rotates very slowly around the sun. So anyway, it's not very nice, and it's small and hot and cold at the same time, depending on where you are. Venus is extremely hot enough to melt lead on the surface, sulfuric acid rain, 90 atmospheres pressure on the surface, so we're not living there. And all the others are made of gas, so we're not living on them either. So I'll go Pluto to annoy everybody, then Earth, Mars. And then it's interesting, so we have 2 missions at the moment on the way to Jupiter's moons, in particular Europa, which is a potential habitat for life. So I'd probably go Jupiter then because of its moons, but Saturn's moons are also interesting, particularly Titan, which is a planetary-sized moon, and Enceladus, which is a moon with liquid water below the surface as well. So I go for those. But if you ask me where would I send a space mission, where would be my number 1 choice, then I would say probably Neptune, because Neptune has a wonderful moon. Actually, that's a photo of it, actually. So that's Neptune, and Triton, as taken by Voyager 2, which took this image when it's the only spacecraft ever to have gone out here. So I would go for Neptune. Uranus, Neptune, I would send missions to, because we've only had 1 mission to them. So there you go. But let's just be really annoying and say Pluto.
Of alien civilizations at all. That might mean we haven't looked hard enough because we haven't looked particularly hard. The galaxy is very big. But it might also mean that civilizations are rare. If you speak to biologists, they will be more pessimistic about discovering civilizations than astronomers, I think. Biologists say, well, but if you look at life on Earth, we have good evidence it was on the planet, let's say 3.8 billion years ago. So let's say it may have begun even 4 billion years ago after the planet settled down and the oceans first formed. It took 4 billion years, let's say, to go from the origin of life to a civilization, which is about 1/3 of the age of the universe. And if you start to say, well, if that's typical and we don't know, then it may be that there are very few solar systems and planets and stars that are stable enough for that long to allow for evolution to do its work and for the single-celled things to go to multicellular creatures and plants and make an oxygen atmosphere and then make a civilization.
we could find something out there, the likelihood of it being as advanced as us are very small.
Well, no,
but it's just a matter of how far we can reach or how far we can see.
Nobody knows. What people do know, I think, is that the Milky Way is probably the boundary of our aspirations. For
this generation or
forever,
beyond.
I think. And
forever?
I think so.
What if we live 100,000 years and people keep evolving?
The galaxy is 100,000 light years across. There are 200 billion star systems in it. So you could just about perhaps conceive in the far future of beginning to spread out into the Milky Way. You could conceive of that. But then you go, well, where's the next galaxy? Andromeda.
Right.
It's over 2 million light years away. I mean, it takes a light beam to 2 million years. So if you want to talk to someone in Andromeda, it will take 2 million years to get a message out there and 2 million years to get it back. So there's a 4 million round trip. That's the nearest galaxy. Would an asteroid destroy Earth? It wouldn't destroy the Earth, but it might make it extremely difficult for big things like us to live on the Earth. So an obvious example is for impacts from space, asteroids or comets. They're pretty much as destructive as each other. And the big dinosaurs were wiped out by such an impact. There's an estimate, actually, that kind of scale of impact that civilization destroying or really affects life on Earth, some of the estimates are one in 100 million years or so, just as a broad estimate, knowing what we know. And it's worth noting that the asteroid that took the dinosaurs out was about, 60-odd million years ago. So, if you didn't understand statistics, you'd say it's time for another one.
Do we have systems in place to prevent that yet? Or
we do. So we have mapping projects. So we think we've mapped all or nearly all of the big asteroids that cross the Earth's orbit. And we monitor them. And we have what's called a keyhole system, which means that because their orbits can change through gravitational interactions with each other or with nudges from Jupiter's gravitational field and things like that. So they can change orbits, these things. And so we have a thing called a keyhole system, which if they go through this point in space, then we get more worried about it when it comes around again, and then we start tracking them more accurately. And we have had a couple of missions now to go land on asteroids, take samples from asteroids. We had an impact mission, which impacted an asteroid. So we are trying or beginning to develop the capability to move one if we need to move it. The problem is comets. Comets are nasty because they're big and they often come in. We don't know they're there, basically. We only see them when they're on the way in. And so if a comet came, and for example, there was a comet called Shoemaker-Levy 9, which hit Jupiter a few decades ago. I can't remember the exact date. But that thing hit Jupiter, and the marks it left in the clouds of Jupiter were larger than the Earth. So you get a sense that these things are nasty things. So we don't want one of those coming because there's nothing we could do, basically. I don't know why I'm laughing.
Webb telescope confirmed the universe is expanding at an unexpectedly fast rate. Well, first of all, why is it unexpectedly fast, and why does it matter?
Well, it matters. I mean, you're right. In some sense, it doesn't matter, but it matters in the future. So the universe is expanding, and we found out a few decades ago that it's accelerating in its expansion. So it's expanding faster and faster.
Do we know why?
We don't really know why. So in astronomy, if you don't know what something is, you just put dark in front of it. So we call it dark energy. So there's something called dark energy, which dominates the universe. That's 3/4 of the energy in the universe or so.
And you know that it's there? Is it measurable?
We know it's there because we measure the galaxies are moving apart from each other faster and faster. So you can make that measurement. And then you infer, therefore, that something has got to be stretching space faster than we expected. Essentially what happened before the Big Bang. If you define the Big Bang as the time when the universe was very hot and very dense, our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. So the idea is the universe was there, in a sense, cold and empty and expanding extremely fast. And that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. It made predictions, some of which have been tested. Some incredible predictions, actually, about the way that galaxies are distributed across the sky, because they're not just random. If you look at the galaxies, they're in sort of flows and rivers of galaxies that cross the sky in a pattern called the cosmic web. And inflation predicted that before it was seen, actually. So it's an astonishing idea.
Particle there that we've discovered, and it has all the right properties to be the predicted standard model Higgs particle.
Please explain what that means.
So the Higgs particle, the idea is basically that early on in the expansion history of the universe, as the universe cooled, it went through something condensed out into empty space. So people call it a phase transition, or it's analogous to water vapor condensing out into ice. As you drop the temperature, it changes into something else, into ice. So in the same way that the theory is that as the universe cooled, something condensed out. So empty space isn't empty. It's full of Higgs particles, if you like. Every square meter of this room is full of the Higgs field. And our fundamental particles, the electrons, let's say, in our bodies, interact with that Higgs field. And in that process, they acquire mass. So it's the mass generation mechanism. It's why some particles are massive, like electrons and quarks, and some things like photons are not massive. They're massless, and they travel through the universe at the speed of light.
Please explain dark matter like I'm a moron. In brackets, I am. It's really easy to explain, actually. Dark matter, when we look out into the universe, we see lots of things. For example, the speed that galaxies rotate, or the way that galaxies interact together, or actually the oldest light in the universe called the cosmic microwave background and patterns in it, which are suggestive of there being some kind of particle. So that's like this stuff, like electrons and things, but some kind of particle that's quite heavy and does not interact with light. So that's why it's called dark matter. You can't see it because it doesn't interact with photons, but it dominates the universe, 5 times as much of it as there is of this stuff, out of which everything we can see is made. So that's what dark matter, the best theory for it. We see it by its gravitational interaction. However, it's not shown, it's not proven that's the case because we haven't detected the particle. And there are experiments everywhere in underground labs and so on, and at Large Hadron Collider at CERN where we're looking for these things, but we haven't seen them. And so that leaves open the possibility that there's something else going on that we don't understand.
Go arbitrarily far into the future by flying around in a rocket very close to the speed of light. So we could come back 1 million years in the future and look at the Earth and find out what had happened. You can't go back. As far as we can tell, you can't build a time machine to go backwards. A way to think about it, for Einstein's theory, there are events, which are things that happen in space-time. Let's say that we wanted to come back here tomorrow, and you can say how much time has passed between those events. In Einstein's theory, the amount of time that has passed is the length of the path you take over space-time between the events. If you're carrying your watch with you, and you go between here and tomorrow, you go this way, you go off and come back again, there's a particular length. Someone else can take a different path, obviously, and so that a different amount of time will pass for them between those two things that happen, just because of that one fact, unless someone goes close to the speed of light, or someone goes near a black hole or something where the space-time is all distorted, then you can get big effects.
There's a lot of discussion about this comet, this remarkable comet. It's called Atlas 3I. That's coming through the solar system. And we're finding more and more out about that comet as we go. It's just going past Mars at the moment. I think it's wonderful that we've got photographs from the rovers on the surface of Mars.
Which doesn't look like much there, to be fair, does it?
You think about what that is. That's a photograph from a robot on the surface of Mars that looked up at the sky and saw that, which we now know is something from another solar system. And there's an estimate a couple of days ago that it might have formed 7.5 billion years ago, that thing. Wow. So it was made before the Earth and the Sun had formed out of a cloud of dust. And it's been on its journey across the Milky Way galaxy. And the thing I find remarkable, it's part of the tour really, it's only 400 years that we were arguing about whether the Earth went around the Sun. It's only 400 or 500 years ago. Now we've sent spacecraft to the planets that Kepler and others were seeing move in the sky. And we're taking photographs of interstellar comets from the surface of other planets in about 400 years. So that, to me, is a remarkable story.
What is déjà vu? I've been asked that before. Déjà vu, by the way, I think it's a property of the way that it's not a real physical property of the universe. It's the way that we perceive the world. But anyway. Why isn't Pluto a planet? The reason is that since Pluto was discovered, we discovered a lot of objects that are very similar size,
in similar orbits or in that region of the solar system. So it is true that there's no reason to distinguish Pluto from a load of other stuff that's out there. And so you have to say, well, what do we mean by, are we going to accept that there are 100 planets? Or do we find a different definition of a planet? Is it what we really mean, big things like Neptune and Earth and Jupiter? And do we really mean these little things, which are much smaller than our moon in many cases? So you could say that Pluto, it's a historical accident. It was the first one of these things beyond the orbit of Neptune, although Pluto does come in actually sometimes inside the orbit with these really strange orbits in the far reaches of the solar system. Just because it was the first one to be discovered, we call it a planet, and then we discover a load more. So that was why, basically. But I think that the history is important, and the thing is that it was demoted from its status as a planet before the New Horizons spacecraft, which was sent to explore it, arrived. So New Horizons was in transit. When it got there, I think if we'd just seen this lump of rock, I suspect you've gone, okay, it doesn't matter. But we found this world that is fascinating, and it's geologically active. It's got glaciers of nitrogen ice and mountains of frozen water. And it's geologically active, by which I mean there are parts of the surface, the famous heart on the surface that was seen, which is not, it's not got craters on it. And if you see anything that doesn't have craters in the solar system, it's new, because things are hitting things all the time. So it's this remarkable world. There's even suggestions it could have liquid water in regions below the surface, which could be a habitat for life. So it turned out to be a fascinating world. And so my view, although I've got loads of astronomy colleagues who would strongly disagree, my view is that the history sort of matters when combined with the fact that it's so interesting as a world that I would reinstate it as a planet. And you can then argue whether you should do that historically and so on. But yeah.